What's up, scholars? Today we're talking about permutations and combinations. So this morning I stopped at Dunkin' Donuts for coffee. You can get the coffees in smalls, medium, larges, or extra larges. There are 4 different kinds of coffee, and they also offer 7 different kinds of flavor shots. How many different ways can I order this coffee? Well, let's make a table, a tree diagram, or some other strategy to find the total number of ways I could order my coffee. Keep in mind, I do not have to add a flavor shot. It could just be regular. So let's look at all the possibilities for just one of the sizes. So let's say I got a small. If I got a small, I could also get one of 4 different kinds of coffees. So again, we're just looking at the size, and then the kind, like decaf, regular, bold, vanilla. So there's 4 different kinds of coffee. 1, 2, 3, 4. 1, 2, 3, 4. And then I can also get one of 7 flavor shots, or I could have no flavor shot, just plain. So let's talk about the flavors. So for excuse me, each of these options, for the size option, and then I pick a type of coffee, kind of coffee, and then I could have no flavor shot, or 1, 2, 3, 4, 5, 6, 7, any of those choices. Whew, this is already becoming a pretty big tree. And that's just for one size with one kind and all of these different options of flavor shots. So I would have to do this again for kind number 2, would also have 8 different flavor shots. Kind number 3, 8 different flavor shots. Kind number 4, 8 different flavor shots. And then I'd have to do that again for the medium and the large and the extra large. That seems like a lot. So instead, let's say, how many different sizes do I have? How many different kinds do I have? How many different flavor options do I have? Flavor options, we've got 8 flavor options. We have 4 different kinds, and we have 4 different sizes. So again, if I wrote all this out, I have to do this all over again 4 more times, plus 4 more times for the sizes. So we're going to multiply these numbers together. And we get 4 times 4 is 16, times 8 is a number I don't remember off the top of my noodle, so I'm going to have to get out my handy-dandy calculator. Or I could just do this, 16 times 8. 6 and 8 is 48, and 4, 128. So there's 128 ways to order coffee. That's a lot. It's a lot of choices. So let's say I finally make my decision, and the barista says, do I want to add whipped cream, chocolate syrup, or caramel syrup? Wow. How many more choices do I have now? I have the same number of choices I had before, but now I can add 3 more toppings. So we've got, same idea, our size, and our kind, and our flavor, and our topping. 4 and 4 and 8. And now I have 3 more choices, right? Whipped cream, chocolate syrup, or caramel syrup. So I'm taking my original 128 times 3. I'm going to get it 4 and 2 and 8. Holy crap. 384 ways. That is a lot to handle in the morning. Yes. So let's summarize what we just did right there. In the fundamental counting principle. Fundamental counting principle. So for the fundamental counting principle, we're going to find the total number of ways to do a process and multiply all of those numbers together. Find total number of ways to do each process and multiply numbers together. So for example, we'll have number of first choice times number of second choice times etc., etc., etc. So let's look at an example here. If you've got 3 pants, 2 shirts, and 4 pairs of shoes, how many different possible outfits are there? Well, what are our total numbers of ways for each process? Total number of pants options. We've got 3. How about the shirts? We've got 2. How about the shoes? We've got 4. And what do we do with those numbers? We multiply. 3 times 2 is 6 times 4 is 24 outfits. That's pretty good for only 3 pairs of pants, 2 shirts, 4 shoes. 4 pairs of shoes. Cool. Alright, in this you try, the photo shows a general form of the Indiana license plate. How many license plate combinations are possible? So this is saying in an Indiana license plate we have 3 digits followed by 3 letters. Me and my coffee. How many possible digits could we put in each of these slots? So we've got 3 slots for digits, digit, 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 and 3 slots for letters, letter, letter, letter. How many possible digits? Well, we could do 1, 2, 3, 4, 5, 6, 7, 8, 9. We can't do 0, but we can do, or sorry, we can't do 10, but we can do 0. So let's try that again. 1, 2, 3, 4, 5, 6, 7, 8, 9 plus 0. So we've got 10 total digits we can use. 10 times 10 times 10. And how many different letters could we use? Well, we could use 26. We have 26 letters in the English alphabet. 26. So we have 10 times 10 times 10 times 26 times 26 times 26. And our handy dandy calculator says that answer is 17,576,000 license plates. That's a good amount of license plates. 17 million, huh? I wonder what that compares to the population of Indiana. Let's see. Population of Indiana. Huh. Well, that looks good. We still got, many more millions of license plate numbers we can use. Pretty cool. Alright. Let's keep moving along. Oh no, there's more choices. As I go to pay for my coffee, I see a sign saying, win free coffee for a year. Choose 4 different digits from 1 to 9 to create a 4-digit passcode. Enter your passcode online, and if you match our secret passcode, you win free coffee for a year. That sounds pretty good. Sounds like something I can do. So, how many different passcodes could I choose from? Well, let's do the same kind of idea here. Our first digit and second digit, and third digit, and fourth digit. How many different options do I have for the first digit? Well, I could do 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9. So I have 9 different choices. But once I've chosen one of those digits, I can't do it again. I can't use it again because it has to be 4 different digits. So I pick one from here. I can't use that one anymore. So now I only have 8 choices for the second digit. And now I've chosen 2 digits, and the third one can't be similar to either one of those. So now I only have 7 choices left. And similarly, I only have 6 choices left for the last digit. Now what do we do with all these numbers? We multiply them. And let's see what our handy dandy calculator says. 9 times 8 times 7 times 6. I've got 3,024 passcodes to choose from. That's kind of a lot. Hopefully I do well. I wonder what my probability of getting that correct is. Let's just say for fun. So I choose one out of those 3,024 passcodes. 1 divided by 3,024. My probability of winning is 0.0003, or if I move my decimal place 2 spots, I have a 0.03% chance of winning. It's not very good, is it? Nope, not very good at all. That's why playing the lottery, usually you don't win. You mostly don't win. Yeah. All right, well, Dunkin' Donuts is thinking about offering a promotion to win free coffee for life. For this contest, the customer has to use all the digits from 1 to 9 to create a passcode. How many ways can you do this? So we have to use all the digits from 1 to 9. So how long is our passcode going to have to be? It's going to have to be 9 digits long. 1, 2, 3, 4, 5, 6, 7, 8, 9 digits long. To use all the digits, which kind of implies I can't repeat them. So I've got 9 choices for the first one, and as soon as I use that, I only have 8 choices left, and then 7 choices, and then 6 choices, and then 5 choices, and 4 choices, and then 3 choices, and then 2 choices, and then 1 choice. And I multiply all these numbers together. Da-na-na-na-na. And our handy dandy calculator says that 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 is 362,880 passcodes. That has significantly worse odds than the other dude. But free coffee for life, man. You might as well try. Alright, this kind of situation where we write out a number times the next lowest number times the next, 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 times the next. That happens kind of a lot in the math world. So we've come up with a shortcut way of writing that so we don't have to write out all of the numbers every time. Which brings us to our next point of order, one of my favorites, factorials. Get out of there, cord. Factorials. Factorial symbol is an exclamation point. So let's say I want to know the factorial of any number n. That equals that number times the next lowest integer number minus, that's a minus sign, times the next lowest integer, and continue on until you're multiplying by 2 and by 1. So for example, 5 factorial is actually equal to 5 times 4 times 3 times 2 times 1, which is 5 times 4 is 20, times 3 is 60, times 2 is 120. So 5 factorial is really 120. I love factorials so much that I refuse to write an exclamation point after a number unless I really mean the factorial. Like I would never tell someone, happy birthday, comma, you're 10 exclamation points, unless they were really 10 factorial years old, which is never going to happen. Alright, so let's evaluate some expressions using our new found factorial. 8 factorial, best number ever. 8 factorial is really 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. How much is that? 8 times 7 times 6 times 5 times 4 times 3 times 2 times 4 is 40,320. We can even do this with fraction things. We got 17 factorial, 17. I'm going to put dots because I'm going to run out of space if I don't otherwise. Can we write it all out? I think we can. I think it's gonna work all the way across my page. Yeah. There's 17 factorial on the top. And 12 factorial, watch what I'm going to do here. I'm lining these suckers up. And why am I doing that? So I can cancel out the things that are the same on the top and the bottom. Bye! So this is actually only now 17 times 16 times 15 times 14 times 13, which is, according to our handy-dandy calculator, 17 times 16 times 15 times 14 times 13, 742,560. Alright, for example, in how many ways can you file 12 folders one after the other in a drawer? Well, I've got 12 folders. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I can put any one of those 12 in the first slots, and then after I've put one away, I only have 11 choices left. And then 10. Wait a minute, I see what's happening here. This is going to be a factorial. Oh yeah. Let's see what 12 factorial is. Ah, my calculator has a factorial button. 12 factorial. Boom. That's equal to 479,001,600 ways. Wow, that is a lot. Alright, so one of the ways these factorials come into play are in permutations. Permutations are the number of ways we can order things. Order items. Okay, that order word is really important. Keep that in mind. And the formula for a permutation is the total number of things that we have, n factorial, over n minus r factorial. And I'll show you how we can use our calculators to get that. In our calculators, we will put in NPR. P is going to stand for permutation, which we will use when we're trying to order items. Where again, this N stands for the total number of items, and R stands for how many items we are ordering, or how many slots we have to order. So the number of items we want. Alright, let's check this out. 10 students are in a race. First, second, and third places will win medals. How many ways can 10 runners finish in first and second and third if there are no ties allowed? We could do this with the fundamental counting principle. Fundamental counting principle. So, how many slots do we have? First, second, and third. We've got 10 runners, so there's 10 people that can win first place. Nobody's allowed to tie, so then there's only 9 people that can win second place, and 8 people that can win third place. First, second, third. Plug those in to a handy-dandy calculator, and we see that 10 times 9, I don't need a calculator for that. 10 times 9 is 90, and 9 times 8 is 7. 20 ways. We could also do this with permutations, because we're trying to put things in order. We are trying to take 10 people and put them in order in 3 different spots. So we'd be doing 10p3, aka 10 factorial over 10 minus 3 factorial, aka 10 times 9 times 8 times 7 factorial. I'm going to show you why I wrote it that way in a second. Over 10 minus 3, which is 7 factorial. I did that so these cancel. We got the same thing again. 10 times 9 times 8. Still 720 ways. Cool. Alright. Well, moving right along. Alright, so I had my coffee for breakfast. Now I'm hungry for lunch. Back in 2009. 2009, Wendy's had a takeout bag that said, "We figured out that there are 256 ways to personalize a Wendy's hamburger. Luckily, someone was paying attention in math class. Is this correct?" Well, let's think about it. Does the order of the toppings matter? For example, is ketchup and then mustard the same as mustard and then ketchup? In terms of taste, yeah, it really is. It's all going to get mixed together. It's all got all the same stuff. So, order does not matter in this case. It's all going on the sandwich, all going in your belly. Order doesn't matter. Wendy's offers 9 topping options for their hamburgers. Choose 3 favorite toppings and list all the possible ways you could put them in order below. Alright, so I like to have, I'm a mustard fan. We're going to have some mustard. We're going to have lettuce. And we're going to have tomato. Mustard, lettuce, and tomato. So all the possible ways they could be put in order. We just said order doesn't matter, but I want to figure out the possible ways we could put those in order. So I could do mustard first, then lettuce, then tomato. I could do mustard first, then tomato, then lettuce. I could do lettuce first, then mustard, then tomato. I could do lettuce first, then tomato, and then mustard. Or I could do tomato first, and then mustard, and then lettuce, or tomato first, and lettuce, and then mustard. And that's it. Those are my possible ways. How many is that? There are 6 possible ways, which is actually the same as 3 factorial. Three factorial ways. Okay. So, how many ways can I order a hamburger with those 3 toppings if the order does not matter? Well, let's use our permutation idea and then divide out the repeats, which are like this. I'm saying this would all be repeats because we said order really doesn't matter. These are how many repeat possibilities of hamburgers I would have of these 3 toppings. So we're going to divide out the repeats from our permutations. So our permutation, again, NPR, and we're going to divide out the repeats. So how many total toppings do we have? 9. We are choosing 3 of them, and we are dividing by our repeats here. If you plug all that into a calculator, we're going to get 9 times 8 times 7 all over 3 factorial, and we get 84 ways. So I don't think they were correct. Someone was not paying attention in math class. Just real quick, I didn't write it out, but these cancel out. This was our full factorial on the top, 9 times 8, 7, 6, 5, blah, 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 blah. And on the bottom, that is the n minus r factorial. 9 minus 3 is 6. 6 factorial, those canceled. But I didn't write it out. So that's where that came from. Okay? Cool. So, what we actually did here is called a combination. Alright, that's a combination. So let's write out the rules for combinations. Combination is the number of ways you can choose a group if order doesn't matter. Number of ways to choose a group if order does not matter. So for combinations, we write that as NCR. That'll be n factorial over what we had before, n minus r factorial. But we're going to divide out the repeats, which was r factorial. So again, n is the total number of choices, and r is the number of items we're choosing. Items we are choosing. So in our last example, we had 9 toppings, and we were choosing 3 of those toppings. So again, difference between permutation and combination. Combination order does not matter. Okay, you're going to finish the last page yourself. Good luck, scholars. Keep on that hustle. See you next time.